Hello, and in these next series of videos we'll be continuing our investigations into time-dependent circuits. Previously we've just considered circuits where the voltage or current sources turn on at some point and remain at a fixed value from then on. This time we're going to be looking at the more interesting cases of those voltage and current sources varying sinusoidally. We're going to start by a quick revision of capacitors and inductors and how they behave when the voltages across them and the currents through them are sinusoidally changing with time. First of all, capacitors. We know that for a capacitor, the excess charge on one plate of a capacitor is related to the voltage across the capacitor by the formula Q equals C times V. From this formula, we can derive that a change in charge must be equal to the value of the capacitance in farads times the change in the voltage that is produced by that change in charge on the plates. And looking at the rate of the change of charge, we could say that the change in charge in a small time equals the capacitance times the change in the voltage in a small time. And as we reduce the small time down to infinitesimal values, this just becomes dq dt, the rate of the change of charge, equals the capacitance times the rate of the change of voltage. Now the rate of the change of charge is the rate at which charge is entering one plate of the capacitor here. By definition, the current. So we have the current equals the capacitance times the rate of change of voltage. For inductors, the corresponding equation is that the EMF, or the effective voltage across the inductor, is the inductance in henries multiplied by the rate of change of the current flowing through that inductor. And those are the two differential equations that we need to solve if we're going to do circuit analysis with inductors and capacitors. Let's consider an example circuit. This one. We can do nodal analysis on this circuit, and that would result in a series of equations which we would need to solve in order to determine the voltages and the currents at every point throughout this circuit. And as with standard nodal analysis, I first label the nodes. I'll call this one A and this one B. The voltage at A, I'll call VA. The voltage at B, VB. I'll label the currents IL, IR, and IC, making sure that I clearly label the directions in which these currents are flowing. I won't bother to label the current through the voltage source because I can see that it's just going to be equal to IL. I then have to write equations for all of these individual components. For the voltage source, the equation is that VA is equal to 1 volt because it's 1 volt above the local reference ground. That's what the voltage source does. The equation for the inductor would tell me that the current through the inductor is related to the voltage across the inductor by VA minus VB is equal to L times DIL dt. The equation for the capacitor, that's I equals C dV dt. So the current through the capacitor here, IC, would be equal to the capacitance, C, times the rate of change of the voltage across the capacitor. Well, the voltage across the capacitor is VB minus 0, so just VB. So that's dVB by dt. For the resistor here, I can just apply Ohm's law, and that would give me that VB minus 0, or just VB, is equal to IR times the value of the resistance R. I'm leaving these with L, C and R for the time being. Now, I don't have to apply Kirchhoff's current law to node A because I've already effectively put that information into my system of equations by not labelling the current through the voltage source here. I could label the current through this voltage source as, say, IV, and then apply Kirchhoff's current law, which would tell me that IV equals IL, but I kind of see that that's a bit obvious, so I'm not bothering to introduce that additional variable. I do, however, have to apply Kirchhoff's current law to node B, and that would give me that IL, the current flowing into the node B, is equal to IR plus IC, the total current flowing out of the node. As the slide says, now what? We've got a system of linear differential equations here. And we're going to have to start solving these by eliminating these variables, the currents and the voltages. However, the currents and the voltages don't appear just as themselves. They sometimes appear as their differential with respect to time as well. So we have to do a bit more work to try and solve this set of simultaneous equations. One way to proceed would be to take the differential of this equation from Kirchhoff's current law, and note that that would tell us that the rate of change of IL with respect to t must be the sum of the rates of changes of the other two currents with respect to t. Then we could substitute from this into here, and if we differentiate this expression as well to get dVB dt equals dir dt times r is just a constant, then we can eliminate IR between these two equations and IL between these two equations. We could then differentiate this equation as well, giving dic dt equals c d squared vb dt, and now replace all of these terms in Kirchhoff's current law equation, or the differential form of it, and that would give us that VA minus VB divided by L is equal to dir dt, which is 1 over r times dVB dt, plus dic dt, which is c times d squared VB over dt squared. Oops. And we know that VA is equal to 1, so I could just replace that VA with a 1. And now I have an equation in only one variable, the voltage at B. However, it's a second-order differential equation, and not a particularly straightforward thing to solve. I will leave the techniques for solving equations like that to the mathematics module. The only point I wanted to make here is that it's quite tricky. This, however, is the general case. There are three very useful properties of sine waves that we can use to make our life a little bit easier if the voltage source was a sinusoidally oscillating source. These properties. We know that differentiating a sinusoidal oscillation gives another sinusoidal oscillation at the same frequency. It may have a different amplitude, it may have a different phase, but it's going to be the same shape. And the same thing is true of integrating. We also have this useful result that adding together two sine waves of the same frequency results in another sine wave at that same frequency. And that's all we're doing in our analysis here. We're differentiating and we're adding up these results. And if all of these things are sine waves, then every result that we're going to be getting is going to be a sine wave. So we have this very useful result for what I've termed linear circuits. A linear circuit being one in which the relationship between the current and the voltages around any component is always either the current is proportional to the voltage, or proportional to the differential of the voltage, or proportional to the integral of the voltage. So everything, if it starts being a sine wave, remains being a sine wave. And Kirchhoff's current law is adding up sine waves, resulting in more sine waves. And everything is just a sine wave at the same frequency. And as long as that is true, we can make a lot of simplifications that make our life much easier. And in a lot of circuits of real importance, this assumption is valid. Next time, we'll be looking in a lot more detail at one simpler circuit, this one. This is a circuit that we've seen before when the voltage source here was just turned on and we got that exponential charging up of the capacitor. Now we're going to investigate it when the source here is sinusoidal. If you do nodal analysis on this circuit, you will end up with this formula for the voltage across the capacitor. And you can solve that differential equation and it will give this result. I won't bother to do that derivation now because in a few lectures' time I'll show you a method in which you can get from here to here much easier than solving any differential equations. For now, have a look at the mathematics notes or just believe me that this is the result. And in the next video, we'll be looking at the consequences of that result.